Today we're going to talk about stars, the nuclear fusion reactions that occur inside of them, and where all the elements come from. But first, let's do a quick review of the atomic structure so that we're all on the same page, and then we can go from there. The center of an atom is called the nucleus, which is made of particles called protons and neutrons. The nucleus of the atom is surrounded by a cloud of particles called electrons, and there are the same number of protons in the nucleus as there are electrons orbiting in that cloud. The electron was discovered by J.J. Thomson in 1897. The discovery was made using a series of experiments where Thomson would pass an electric current through a vacuum tube and observe how the current behaved in the presence of electric and magnetic fields. You can see his experiment being demonstrated here. Notice that when the positive end of the magnet is placed near the glass tube, the electric current bends toward it, and when the negative end of the magnet is placed near the tube, the electric current bends away. He then used these experiments to confirm the electric charge and the mass of a small particle he called a corpuscle, which we now know today as the electron. The proton was discovered by Ernest Rutherford in 1918, and I actually already made a video describing this, sort of, so if you want to, feel free to go watch it at any point. The existence of the neutron was actually predicted by Ernest Rutherford as well in 1920. He made the speculation because when he added up the individual masses of the electrons and protons within an atom, it was quite a bit less than the mass of the overall atom itself. The actual existence of the neutron was confirmed by James Chadwick in 1932 while he was doing some investigation on a new type of radiation. He was able to determine that the radiation was composed of uncharged particles that had about the same mass as the proton. The periodic table is a tabular arrangement of the known chemical elements. The periodic table is a tabular arrangement of the known The periodic table is a tabular arrangement of the known chemical elements based on their atomic number, their electron configuration, and their chemical properties. It was published by Dmitry Mendeleev in March of 1869. At that point in time, not all the elements had been discovered, so the table had gaps in it. But because of the way the elements were organized in the table, the gaps not only predicted the existence of unknown elements at that point, it actually described the properties of these unknown elements, all of which were eventually found. So in case you haven't seen the periodic table, this is what it looks like. As you can see, it's made up of a bunch of different squares, each of which represents a different chemical element. If you look at just one of the squares, you'll find a certain amount of information about that particular element. The top number is called the atomic number. It's the number of protons in the atom's nucleus. The bottom number is called the atomic mass. It's the average number of protons and neutrons in the atom's nucleus. And the letters in the middle there are just the chemical symbol. They're just the letters used as a form of shorthand in chemical equations. So for the majority of this video, I'll be talking about nuclear fusion. But just real quickly, I wanted to describe the differences between nuclear fusion and nuclear fission. It's the splitting of an atom's nucleus. It's usually done with uranium-235 because it's the only fissile isotope found in any kind of quantity here on Earth. Like other heavy elements, it has a lot more neutrons than protons in its nucleus, which makes it very unstable. When bombarded with neutrons, a uranium-235 nucleus will split into two smaller particles. It will also emit a certain amount of energy, and at the same time will eject some of its own neutrons. These neutrons will then collide with other uranium-235 nuclei, and the process happens again. Each time this repeats, more and more nuclei are split, releasing more and more energy along with more and more neutrons, in a chain reaction that if left uncontrolled could potentially level an entire city, as demonstrated in Japan in August of 1945. After the nucleus splits, the sum of the mass of the resulting particles will be less than the mass of the original uranium nucleus. This apparent loss of mass is described exactly by Einstein's famous equation E = mc², which tells us that a small amount of mass is being converted into pure energy. And in the case of an uncontrolled fission reaction in an atomic bomb, we're talking about a lot of energy. It's just the joining of two or more atomic nuclei. At a sufficiently high temperature and pressure, Two or more atomic nuclei can slam together to form a new type of atomic nucleus. The resulting particle has a total mass that's less of the combined mass of the particles that smash together to form it. This apparent loss of mass can be accounted for using Einstein's equation E=mc². A star begins its life as a giant collapsed ball of gas called a protostar, which is made up of about 75% hydrogen, 23-ish% helium, and 2% trace elements of whatever else happen to be present in the nebula that it formed out of. Once a protostar becomes massive enough, its internal temperature will become so hot that its core will undergo a phase transition into a state of matter we call plasma by a process called ionization. These gas molecules inside of the star's core become ionized when electrons have so much energy that they're no longer bound to their respective nuclei. So at this point, the plasma contains positively charged ions and freely roaming negatively charged electrons. A star lives out most of its life in a state that astronomers call the main sequence. Since the moment of the star's birth, gravity is constantly trying to collapse it down on itself. But during the main sequence, the energy produced in the star's core produces an outward pressure that exactly counterbalances the inward pressure of gravity. We can determine the chemical composition of a star by using a technique called spectroscopy. The way this works is that you shine the light from a star through a prism which breaks it into the different colors of the rainbow. And looking very closely at this rainbow pattern, you'll find dark bands in the spectrum where certain colors of light are missing. This corresponds to the different wavelengths of light that are being absorbed by different elements in the star. Since these absorption lines are different for each individual element, we can use the lines as a kind of fingerprint to determine what elements are present in the star. For example, hydrogen has a different fingerprint than helium does. So when we shine the sun's light through a prism, we can pretty easily see the fingerprints of hydrogen, helium, and other trace elements, which is how we know that they're present in the sun. The 19th century philosopher Augusta Whatever insisted that we would never know the chemical composition of stars, and that it would always be hidden from us. But as we've just learned, despite his skepticism, it wasn't too long before we were able to solve this puzzle using spectroscopy to identify different elements in the starlight. So there are about 25 elements that are essential for life. Our DNA is formed from atoms of carbon, nitrogen, oxygen, phosphorus, and hydrogen. To form proteins, we need to add sulfur to this list. We need iron to form the hemoglobin that transports oxygen around our body. Calcium is required for your bones. Sodium and potassium are needed for the transmission of impulses along your nerves, and you get the idea. It's an amazing fact that, with the exception of the simplest atom, hydrogen, all of the atoms in our bodies were cooked up in the core of a star. You may have an atom in your left hand that was made in a star in some random corner of the universe, and an atom in your right hand that was made in a completely different star a million light years away. Think about that. Working out how the chemical elements were synthesized in stars was one of the greatest scientific achievements of the 20th century. But this party didn't just start in the 1900s. To tell this story, we're going to have to rewind the clock about 13.72 billion years, back to the Big Bang. Within the first few minutes after the Big Bang, almost all of the matter in the universe was about 76% hydrogen nuclei, 24% helium nuclei, and then small trace amounts of lithium nuclei. These are what we call the primordial elements. After about 300,000 years, the universe had cooled and expanded enough that electrons were finally able to fall in line with these primordial elements to form a transparent mix of hydrogen and helium at about a ratio of 3 to 1. Using a slightly uneven distribution of just these elements plus a little gravity, and we've got exactly what we need to start writing the book of Genesis. All of the elements that we see in the universe today were created as a kind of byproduct of the process that stars use to keep themselves shining. But before we dive into how stars generate their power, we need to do a quick review on the forces that are critical to understanding nuclear fusion. The strong force is exactly what the name suggests. It's a very strong force that binds quarks together to form protons and neutrons, which themselves form the nucleus of atoms. The weak force, as its name implies, is relatively weak, but only because it's such a short-ranged force. The weak force is mainly known for its role that it plays in radioactive decay, but it also provides a crucial interaction that's responsible for the formation of atomic nuclei, which we'll talk about in just a minute. The equation E=mc² is found in Einstein's 1905 publication of his theory of special relativity. In the equation, the E stands for energy, m is mass, and c is the speed of light. Prior to the acceptance of special relativity, mass and energy were thought of as two completely separate things, but Einstein came along and proved mathematically that you could convert mass into energy and vice versa. While developing his theory, Einstein found that the ratio between a mass to energy conversion was exactly the speed of light squared. This is a huge number. So if you wanted to find out how much energy would be produced by converting a certain amount of mass into pure energy, you would first take the speed of light, which is 186,000 miles per second, or about 6 trillion miles per year, and multiply it by itself, square it. Then you take that gigantic number and multiply it by the mass in question, and that would be the energy released. So as you can see, even a small amount of mass can be converted into a huge amount of energy, which is what we find happening at the core of our sun and other stars. In the 1920s, Arthur Eddington suggested that a star's power comes from nuclear fusion reactions happening in the star's core, and then set out to prove it, which he did successfully. Now, most of the time, people talk about the sun's energy being produced from the fusion of hydrogen into helium. Now, to be clear, this is called nuclear fusion and only involves the nucleus of the atom. But before you can fuse a hydrogen nucleus into helium, there's a crucial intermediate step that must happen, which is controlled by the weak nuclear interaction we mentioned earlier. So what we're going to do is describe the steps necessary for the nucleus of a hydrogen atom, which is just one proton, to undergo nuclear fusion and end up becoming the nucleus of a helium atom, which is 2 protons and 2 neutrons. Alright, so here it is. 2 protons can get close enough to each other for a fusion reaction to occur only if they're moving at extremely high speeds, which is facilitated by the very high temperature in the core of the sun, which is about 15 million degrees Kelvin. So even though the strong nuclear force will bind together collections of protons and neutrons, it's not quite strong enough to form a nucleus from just 2 protons. Without the additional glue provided by a neutron, the electromagnetic repulsion between 2 protons is a little too strong. So this means that for the first step along the road to a helium nucleus, 2 protons must be forced together in a high-speed collision, and at the exact moment of impact, one of the protons must simultaneously undergo a weak nuclear interaction known as inverse beta decay. During this process, the proton converts into a neutron by emitting a positron and a neutrino. The other proton and the newly formed neutron then bind together to form a nucleus of heavy hydrogen, which is an isotope known as deuterium. This is that critical step I was talking about that's responsible for the elements and the liberation of energy within stars. Without the weak interaction that converts one of the protons into a neutron, there would be no matter in the universe other than protons and electrons. The universe would consist entirely of hydrogen and nothing else. However, the extreme weakness of the weak force makes this step exceedingly slow. Just one collision in 10 billion trillion between 2 protons in a star such as the sun results in a fusion reaction. Typically, a proton will race around ricocheting off other protons for millions of years before it undergoes this reaction. So this is the bottleneck that determines the overall rate of conversion from hydrogen to helium. Even though a typical proton will have to wait for freaking ever before undergoing this reaction, the quantity of protons in a star is enormous, and the production of deuterium proceeds steadily throughout the star's life. The next step in the process happens almost immediately. Within 1 second, the deuterium nucleus captures another proton to form a nucleus of light helium containing 2 protons and 1 neutron, and in the process emits a gamma ray photon that carries away most of the energy produced in the reaction. On average, it will take another million years for the helium-3 nucleus to collide with another helium-3 nucleus and undergo the next step in the reaction by ejecting 2 protons, which leaves us with a typical helium-4 nucleus. And the synthesis of helium-4 nucleus is responsible for the vast majority of the energy produced by the sun. Every second, 655,000 tons of hydrogen are fused into 650,000 tons of helium, resulting in 5,000 tons of mass being converted into pure energy, which is emitted as electromagnetic gamma radiation that ultimately heats up the Earth, making it hospitable for life to evolve. The mass of a star is directly related to the elements that it can produce in its core. The greater the mass, the greater the gravitational pressure, the higher the temperature, the more elements it can cook up inside. For stars like our sun, nuclear synthesis can't happen much past helium. Such a star will eventually produce carbon, nitrogen, and oxygen, but nothing more. Once our sun exhausts its huge reserves of hydrogen, the core won't be able to produce enough energy to keep itself from collapsing. Its core will continue collapsing into an extremely dense, hot body known as a white dwarf, while the outer regions float off into space. The white dwarf left behind is effectively the glowing ember of the core of the star and will be about the size of the Earth. Nuclear reactions have stopped inside of it, and the star will gradually cool as it radiates its heat off into space. even though stars like our Sun don't do much in the way of creating the more complex elements, and the way they die is considered by most to be kind of disappointing, more massive stars are able to synthesize much heavier elements, and the way they die is awesome. When a heavyweight star has consumed all of its hydrogen fuel, it undergoes gravitational collapse until its core reaches a temperature high enough that it can begin a new phase of nuclear fusion reactions, and the energy generated here will prevent the star from collapsing even further. Meanwhile, the outer layers of the star have expanded into what we call a red supergiant, and will typically become as large as the orbit of Jupiter. So now it's time for these massive stars to start fusing helium nuclei together, but there's a problem. The helium nucleus is super stable, which is why so much energy is produced when it's fused together. But its stability is what makes further fusion reactions very difficult. You might think at this point that we just need to smash two helium nuclei together to create element number 4 on the periodic table, beryllium. But unfortunately, this is kind of like trying to smash two protons together. They won't stick. They require that additional glue that's provided by a neutron. So to take the next step in the periodic table past helium, it's actually necessary that 3 helium nuclei collide to form element number 6 on the table, carbon. As you can probably imagine, these triple collisions are very unlikely events, and are actually only possible if the helium nuclei collide at extremely high temperatures. We're talking 60 million degrees Kelvin, which is hotter than the core of our Sun and can only be achieved in extremely massive stars. At these temperatures, the carbon nucleus will also fuse with the helium nucleus to form element number 8, oxygen. When the helium fuel is depleted, the star's core will once again undergo gravitational collapse, increasing the pressure and temperature up to about 100 million degrees Kelvin, which triggers the next stage of nuclear fusion reactions. At this temperature and pressure, oxygen and helium will begin to fuse together to form element number 10, neon. Neon will then fuse with helium to form number 12, magnesium, which is what plants use to collect the sun's rays and is the starting point for most food chains here on Earth. As this pattern continues, the heavier nuclei will continue to sink toward the middle of the star, so that the core will eventually start to resemble something that's layered like the inside of an onion. Once all the carbon has been consumed, the star's core will once again undergo gravitational collapse, pressure increase, temperature increase, and will trigger new nuclear fusion processes that produce element number 14, silicon, and number 16, sulfur. By this point, a wide range of lighter elements are being cooked up in a complex layer system of different nuclear reactions. However, there is a natural endpoint for the stellar nuclear fusion, and it stops at iron, element number 26. Iron is the most stable atomic nuclei and won't fuse together to form any new elements. This is because the amount of energy required to fuse iron nuclei is greater than the amount of energy produced during the fusion reaction. This of course means that no more energy can be generated in the star's core involving iron nuclei. And without the continued release of energy, the outward pressure preventing the gravitational collapse can't be maintained. And the consequence of turning off the nuclear fusion reactor at the core of a star is a gigantic explosion we call a supernova. Once a supermassive star runs out of fuel, it collapses in an instant. Within about 1 second, the entire star can be squeezed down into a ball with a diameter about the size of a major city, like London. In the final milliseconds of the collapse, protons and electrons are forced together until they interact through the weak nuclear force and essentially merge into neutrons. At the same time, a ton of tiny particles called neutrinos are emitted, and the result is a star that's composed almost entirely of neutrons. The star is called a neutron star and has basically turned itself into a gigantic atomic nucleus. Neutron stars are so dense that just a teaspoonful of its material would weigh about 2 billion tons. The collapse of a massive star into the very tiny volume of a neutron star involves enormous amounts of gravitational energy, which essentially rebounds, sending shock waves that plow through the outer layers of the star. This shock wave is followed up by a huge blast of neutrinos and gamma rays that fly outwards through those outer layers of the stars, transferring massive amounts of energy and momentum. This ignites the explosion and provides the necessary conditions that are perfect for cooking up elements heavier than iron, such as nickel, copper, and cerebral desecration. Wait, no, that's a different type of heavy metal. But anyways, that's what we see as a supernova and is where the rest of the heavier elements come from. So just real quick, I want to send a shout out to the guys in Cerebral Desecration who let me use some of their music for this video. They're a band based out of San Marcos, Texas, and they make some awesome music. So if you're into metal and hardcore, click right here, go check out their YouTube channel. They just recently put up a new music video which is badass. I'll also put a link to their Facebook page in the description below, so go check that out when you get a chance.